Good morning. I'm Gioele Gottardo, and today I'm going to present PerfDojo, an automated machine learning library generator for heterogeneous architectures. So we know that the massive size and complexity of modern machine learning models require exponential increase in computing power. And this led from one side to the growth of specialized high-performance accelerators like GPUs, TPUs, and FPGAs. And on the CPU side, we saw a constant evolution of the processor architecture to integrate new extensions for AI workloads. Fully utilizing the peak performance of these varied and specialized systems is becoming increasingly difficult. On top of that, this problem is amplified for machine learning because of the growing number of new models and new kernels with new techniques like sparsity and quantization. And the problem is that manual optimization is very expensive. It demands significant man hours just to acquire the necessary architectural expertise. And existing automatic optimization frameworks still fail to match the performance of hand-tuned libraries. Now, for these reasons, we propose PerfDojo, which is an abstract code transformation environment for hardware-specific optimizations. Our main insight from PerfDojo is that despite the variation in implementation, common optimization strategies such as tiling, vectorization, and the use of specialized instructions remain prevalent when optimizing kernels. And in PerfDojo, we provide an abstraction to those strategies and an environment that ensures correctness when applying the strategies. And once we have such an environment where we can apply transformations to code, we can study several automatic methodologies to select the transformations. And we propose PerfLLM, which is one of those methodologies that use large language models and reinforcement learning to automate the code transformation selection. Now, to create PerfDojo, we start by looking at what a performance engineer usually would do when developing a kernel. So usually the engineer will write the code for a given kernel, then compile it and run it and measure the performance. If the performance doesn't match what they expect, they would then rewrite the kernel until they get the performance that they need. And we try to provide a more systematic approach to this optimization process by providing this transformation-based optimization loop. So in PerfDojo, we provide a library of transformations that can possibly provide benefits to a given kernel. And the user is tasked to select the transformation that they want to apply. Once the selection has been made, PerfDojo will find a set of locations where the transformation can be applied without breaking correctness. And again, the user here will either manually or automatically select the location where they want to apply the transformation. And once we have both the location and the transformation to be applied, the system will apply the transformation and generate the code. And again, this process can be iterated to obtain an optimized, final optimized kernel. And very crucial for this system is again the semantic preservation, so that we can safely apply the transformations without worrying about the correctness. And this is especially important for an automatic system like PerfLLM that really uses this safe environment to automatize the selection of transformations. And PerfLLM more specifically uses large language models and reinforcement learning to select the best transformations for a given kernel. So in this system, we first convert a kernel description into an embedding using a large language model, and this embedding represents the state of the system. Then we define an action as a pair of embeddings that represent the kernel before and after the transformation. And we also define the reward for the reinforcement learning system as a constant C over the runtime of the kernel. So once we have the state space, the action space, and the reward, we can define a reinforcement learning system that will learn how to select the best available transformation. And again, we can repeat this process over and over again until we have selected all the transformations that lead to a final optimized kernel. Okay, so this was an overview of the whole system. Now let's dive deeper into PerfDojo and see how we represent kernels in PerfDojo and how we transform them. To do so, we use a very simple example. In this case, is the softmax kernel that in C could be implemented like this. Now, in PerfDojo, we represent this kernel with the following ordered tree. So in this tree, each internal node is a loop, and the leaves are the operations. And this is the corresponding textual representation for this kernel. This is very important because it is what we feed to the large language model to summarize and create the embeddings. For the transformations, we use even simpler kernel. And this kernel, what it does, it's a simple copy, actually two copies. We copy tensor X to temporary tensor T, and then we copy the tensor T to the output tensor Y. And with this first implementation, the generated code will have two nested loops with single copies inside. And one of the possible transformations we can apply here is the join scopes transformation that will join the two outermost scopes. And the resulting C code after this transformation is what we can see here. And we see that now the two outermost loops are merged into a single loop. Once this transformation has been applied, a new transformation becomes available, which is the reuse dimensions. And what this transformation does is to reuse one of the dimensions of the tensor T. And this will allow us to reduce the size of T from 24 to 6. And very importantly here, we cannot apply the reuse dimensions before applying the join scopes. And this is one of the examples where we really enforce correctness on the system. Because if we would allow to apply these transformations in the initial kernel, this would lead to incorrect code. Again, this was a very simple example of the transformations, but we have many more transformations and they are listed here. And again, for each one of these transformations, we have applicability detection. I mean, some of the things that these transformations do are, for example, like modifying the loop structure or the memory layout, or they implement parallelism, or using hardware-specific features. Okay, now let's evaluate PerfDojo. First, starting with some existing architecture that has been already well studied. And what we want to demonstrate is that PerfDojo can reach competitive performance compared to other tools on this well-known architecture. And for this, we use the x86 architecture, and we use an Intel CPU. And we compared PerfDojo to several systems. First one, we compared the Onyx runtime, and we also implemented these kernels in JAX and used the just-in-time compilation to compare it with PerfDojo. We also looked into Pluto, which is an optimizer that uses the polyhedral model. And we compared those to TVM using both a simple optimization pass and a search with 1000 evaluations. And finally, we compare it also with the 1DNN library. And we can see that with PerfDojo, we can apply several techniques that are competitive with existing systems. The first one is a heuristic, where we apply all the transformations that are available in a somewhat naive way. Then we also implemented the search similarly to TVM that will use either greedy or search or simulated annealing to find good transformations to be applied. And also we show the results for manually transforming the kernels, where the user manually selects the transformations they want to apply. And as mentioned, these results show that our system can achieve competitive performance to other tools and even beat TVM on using the search. And we actually obtain a 7.6 improvement over TVM. Now we have proved that PerfDojo can provide performance for existing well-known architectures, but we also want to prove that our method can be easily extended to novel architectures. And here we show some of the kernels that we have implemented. And again, we can study several optimization strategies to optimize the kernels. Here we show first a naive implementation, a naive strategy, where we use only non-hardware specific transformations. And we also show a greedy strategy where we greedily select all the available transformations, including the hardware specific for the snitch architecture. And we also provide an heuristic that, knowing the architecture, it will make some smarter decisions about which transformation to select. And here we show that we can implement many kernels for this novel architecture, but we also compared it with the handwritten kernels from the developers of Snitch. And we show that even there, we can beat the handwritten implementations by 13%. And again, here we show only some of the kernels, because at the time of this work, these were the only kernels available for the architecture, but we were able to extend them using the PerfDojo system. Now, after we proved that with the correct transformations, PerfDojo can obtain competitive performance for both existing architectures like the x86 CPUs and for novel architectures like Snitch. We want to demonstrate that PerfLLM now can efficiently use large language models and reinforcement learning to find the correct transformations that achieve that performance. And so we run our transformation search with PerfLLM on a set of deep learning kernels, and we compared the results with PyTorch and TVM. And here we show the results for an x86 architecture, where we achieve a 1.5 speed up over PyTorch 1.8 over TVM. And if you compare it on an ARM architecture that received less attention from library implementers, our results are even more impressive, with the geometric mean speedup of 6.6 over PyTorch and 13.6 over TVM. And this again shows how this method is applicable regardless of the hardware architecture. And in conclusion, we introduced PerfDojo, a safe code transformation environment to optimize machine learning kernels. And on top of PerfDojo, we built PerfLLM that uses large language models and reinforcement learning to select the best code transformations for a given kernel. And we showed some examples on how this transformation-centric workflow works. And we proved that with the right selection of transformations, we can reach competitive performance on both existing and novel hardware like Snitch. And finally, we showed that PerfLLM can automatically find these transformations that achieve great performance, and it can beat TVM and PyTorch over two architectures. If you're interested in this topic, I would recommend you to check out the paper, or in general to listen to other talks from our YouTube channel.